Welcome everybody to the 7th lecture in our course, and today we'll be talking about network analysis. We know circuit analysis, which is like applied for circuits that is operating at lower frequency. At lower frequency, the dimensions of component is much smaller than the wavelength, so there is no phase variation for current nor for voltage across elements, so that we can define a unique voltage and current at any point in the circuit, and we can apply what we know about circuit theory like Kirchhoff's law, Ohm's law, Ampere's law, and this is very useful and powerful in analyzing circuits at low frequency. When we go at higher frequency, the assumptions for circuit analysis at low frequency are not in general valid, and we need to think about new set of rules to analyze microwave circuits, and this is the topic of our lecture today. Why do we need like microwave circuit analysis tool? Why don't we go for like field analysis, like using Maxwell's equation? There is a couple of reasons for that. For example, like Maxwell's equation and field analysis is very comprehensive, and usually it gives us like a lot of details that we might not be interested in. For many microwave circuits, actually what we are interested in are a couple of parameters at the boundaries, or what we call it like at the ports of like the circuit. And having like a microwave circuit tools to do this analysis is something very powerful, much faster than using like field analysis. Field analysis is still needed and used in many different cases for microwave applications, but for circuits that does have sort of like a path, like a clear path for the signal, like transmission line and waveguides, sometimes or in many cases, like we are interested in certain parameters at the terminals or at the boundary of the circuits, and for that reason microwave circuit analysis is needed. Part of the education of microwave engineer is to be able to decide when to use field simulation or field analysis, and when we can apply, or when can we apply the microwave circuit tools that we're going to discuss in this lecture and next lecture. So in order to like analyze microwave circuits using some tools similar to the circuit theory, we need to define voltage, current, and impedance so that we can handle like this analysis. At microwave frequencies, the measurements of voltage and current is difficult unless like clearly defined terminal pairs is available. In general, for TEM modes, the definition of voltage and current is clear and... Sorry, I got an interruption by a phone call, but anyway, I switched my phone silent now. We were talking about the like definition of voltage and current, and I were saying that for TEM modes, this is like very clear and like well-defined parameters. Like TEM modes like exists in coaxial cables, in microstrip lines, in transmission line in general, but this definition for voltage and current and like ratio between them is difficult for single conductor waveguides like circular or rectangular waveguide. So like let us handle first the easier case, which is a TEM transmission line like coaxial cable or parallel transmission line or microstrip or strip line. In those cases, like this general case of two conductors, one conductor would be the positive, the other is the negative. So the potential difference is like path independent between any point on the positive conductor to any point on the negative conductor. So the definition for the potential in this case is very well defined. And for the current, the total current can be calculated through Ampere's law by taking any contour that is like encompass the conductor that's carrying the positive voltage and not including any part of the conductor carrying the negative volt. So like any of those contours here, if we do the integration along this contour, we would calculate the current of this like the mode or transmission line or TEM. In this case, the voltage is well defined, the current also is well defined, and we can define the impedance between, or like, sorry, the impedance of this signal, which is voltage over current. So the case of TEM mode on waveguide, like coaxial waveguide, or on transmission line, like the strip line or parallel lines or any other transmission line, is a well-defined case, and we have a definition, clear definition for voltage, current, and impedance. For cases that is not TEM, like TE10, we have like the field distribution is something like that, and there is no clear definition or unique definition for voltage, current, and impedance. For example, like which voltage, the voltage between this point and that point, which is 0, or from the middle, or what. So there is no clear definition for voltage and current, and if we want to apply like microwave circuit theory or like network analysis tools or mechanism, we need to find a definition for voltage, current, and impedance in this case. And this is what we're going to discuss in the next slides. As I said, there is no unique definition for voltage and current and impedance for non-TEM lines, but there is some general rules on how to define this. So if we fulfilled those rules, then we have a definition for voltage and current that we can use in the network analysis of microwave circuits. So the first one is that the voltage and current are defined for particular waveguide modes. So if we have like more than one mode propagating, like TE10, TE20, so on and so forth, no, we are talking about like a single mode. So for each mode, we would have a definition for voltage and current. Also, in order for the defined voltage and current to be useful in the network analysis, we need the voltage and current to be proportional to the transverse magnetic field, the field in the transverse plane. Also, we need the voltage and current should like be defined so that their product gives the power. So like VI asterisk, the multiplication between the voltage and current, would give us the power flow of the waveguide mode. The ratio of voltage and current for a single traveling wave, single mode, should be equal to the characteristic impedance of the line. This impedance may be chosen arbitrary, but many times we are choosing it to equal the wave impedance, or sometimes normalized to unity. So we have like rules that voltage and current are defined for a single mode. It is proportional to the transverse field. Their product should give the power flow of the mode. Their ratio is the impedance, and we have here like 1 degree of freedom. We can choose the ratio to be like the characteristic impedance of the line, or we can use it like any other value like unity. When we do that, we have a definition for voltage and current that can be used in network analysis of microwave circuits. So here, let us like do like these rules, or put those rules into mathematical form. The transverse electric field in general does have this expression, and if we applied the rule, we would have the volt to be proportional to the transverse electric field. So we have like this definition. We can relate voltage and electric field in the transverse plane with this constant. Similar thing for the magnetic field. In general, it does have this expression. The negative sign here is just to like fulfill the relationship like of the power flow. We know that E equal N cross H. So that like, which is this rule here, the direction of propagation, and the electric and magnetic field are related with this orthogonal rules. That's why we have a negative sign here. You can review the plane wave properties to find why do we have like a negative sign here for the wave propagating in the negative z direction. If we also applied the rules for current and having the current to be proportional to the transverse magnetic field, would have this expression here. And we have those two constants. They are related to the voltage and electric field in that like relations here. So this formats making the equivalent voltage and current proportional to the transverse electric and magnetic fields. And if we write it V and I, we'll have like this expression here. Now we go for the next property, which is the power. We need like the power in general in this case does have this expression which give us like this mathematical expression. As we said, we need our voltage and current product to equal or to be related to the power flow. So we need V multiplied by I conjugate divided by 2 because it's an alternating current to equal the average power. So in this case, what we have, like we need to have like C1, C2 to equal this integration here. So this is the second condition. The third condition is related to the characteristic impedance. We can define the characteristic impedance as V plus over I plus or V minus over I minus, which will give us C1 over C2. So based on that, we have like C1 multiplied by C2 equal this integration, and we have C1 over C2 equal this the characteristic impedance, and this relation, this proportionality, gives us like a degree of freedom. We can choose C1 over C2 to equal Z naught or to equal Z wave or to equal 1. So we have, as I said, like 1 degree of freedom here that we can use to choose like C1 and C2. Once we did this case, like this formulation, now we have an expression for V and I as well as Z that can be used for network analysis of microwave circuits. Here we have an example. Just to apply those rules, we need to find the equivalent VI for TE10 mode in a rectangular waveguide. So the waveguide field does have this expression. You can review the waveguide lecture. The power flow does have this expression. Now we need to define voltage and current in that format, such that the power equals the multiplication of the voltage and current conjugate. So we need to find the relationship between V plus and A plus, V minus and A minus, as we saw in the previous slides. So to find C1 and C2, that relates the equivalent voltage and current to the parameter A, we can equate the incident power in that format, and we can choose Z naught to equal the wave impedance for transverse electric mode. This way, C1 over C2 will equal ZTE, and if we apply those two conditions, we'll find that C1 equals the square root of AB over 2, C2 equals the square root of AB over 2 divided by the wave impedance for TE mode. So with this choices of C1 and C2, we fulfilled the three needed conditions for the definition of V and I to qualify this mode to be used for network analysis of microwave circuits. So this discussion here, I don't intend to examining you in, but just giving you a needed background to prove that network analysis can be done also for waveguides that are carrying non-TEM modes. So it's mainly those slides is to give you enough reasoning that what we are discussing here for network analysis is general and wider than just using it for transmission line networks or circuits and circuits of waveguides that composed of two conductors like coaxial waveguides. No, it is more general, and this discussion here is showing the methodology used to apply the same network analysis tools that we're going to discuss to even for a single waveguide networks. Okay, now we're going to discuss the first kind of tool, or the first two kind of tools, which are the impedance matrix and admittance matrix. So the idea here is that we have a general N-port network. So this network does have N ports. Each port would have some incident volt and reflected volt, input current and reflected current, and this is for each port in the network. So if the network is composed of TEM transmission line or waveguide, it's okay. If it's non-TEM modes, we just discussed the methods how to define the equivalent voltage and current. So here, this theory relates to the terminals or port quantities, the voltage and current, real voltage and current like the case of TEM mode, or equivalent voltage and current like the case of non-TEM mode at the terminal. So the terminal is defined here. The ports may be, as I said, transmission line or transmission line equivalent. So this note here is an important one. If we have a port that is physically a single port, for example, a single rectangular waveguide, but the frequency is higher than the cutoff frequency for two or more modes, so the waveguide would carry multiple modes. In this case, this one physical port need to be like represented by 2 or 3 depending on the number of modes propagating on this like physical port. So if we have like a single rectangular waveguide port that's carrying 2 modes in the network, we need to present this with 2 ports, 2 logical ports or 2 electrical ports. So this note here is important. And also, like at a specific point in the nth port, we define like Tn. Tn is like, the name is like the reference plane or the terminal plane. So this is important for the definition of the voltage. So this is the 0 volt, the definition of the phase. So this is the 0 phase plane. This is the terminal plane or the reference plane. And for each port, we define a specific physical plane to be the terminal plane or the reference plane, where we define the phase at this plane to equal 0. So if we have like n terminal plane, if we have like n terminal network, the nth terminal plane, the voltage and current is defined like this. Vn is the wave propagating inside, like to the inner of the port. V minus is the reflected from the port. Current plus is current going in the port. Current minus is the current going out of the port. So the total voltage at terminal N equal V plus V minus. In is defined as the current going in the port, which equal I plus minus I minus. The first tool for network analysis is the impedance matrix, which relates the voltage and current in the regular way we know. The voltage equal impedance multiplied by current. So V1 is the total voltage at port 1, V2 is the total voltage at port 2, Vn is the total volt at port N. Current is the current going in port 1, I2 is the current going in port 2, so on and so forth. And we have this matrix Z11, Z12, so on, so forth. And this is like a network analysis tool. If we are relating current to voltage, it will be the admittance matrix that we're going to see in the next slides. So the definition of Zij, if we take any element here, Zij, the definition is that it's equal to the total voltage at port I divided by the input current at port J when all currents equal 0 except for port J. So if we are saying this in word, Zij can be found by deriving port J with current Ij and open circuit all other ports. So Ik for all other ports except for port J equals 0. And under this condition, we measure the open circuit volt at port I. So if we put all like the ports to be open circuit, except for example like port 2, so I1 will equal 0, In equals 0, all I's equal 0 except I2. Under this case, we can find Z12, Z22, Z32, so on and so forth. So this is the definition in words, and this is the mathematical expression for Zij. The admittance matrix is relating the current to the volt, and of course the admittance matrix is the inverse of the impedance matrix. So ZII is known as the input impedance seen looking into port I when all other ports are open circuit. So just I is having some current going in, all the other ports does have like an open circuit, so all other I's except for II equals 0. Zij is called the transfer impedance between port I and port J when all other ports including port I are open circuit. So the only port that is not open circuit is port J. Let me like do this. Similarly, the definition for Yij is equals the total input current at port I divided by the potential or the total voltage at port J when all the other ports are short-circuited except for port J. So Yij can be found by deriving port J with certain voltage and then short-circuit all other ports, and under this condition measure the current at port I. So this is the definition and explanation for the terms of Y and Z matrices. So in general, Zij and Yij elements may be complex. So each, if we have like an n-port network, Z and Y are n by n matrix. So each element, each matrix does have n square elements, and each element can have real and imaginary. So we have like two n square independent quantities or degree of freedom for each matrix. But in practice, there is some conditions that make the degrees of freedom smaller or the number of unknowns smaller. For example, like reciprocity or reciprocal and lossless. If the network is reciprocal, we would have the off-diagonal elements to be identical. So like this, almost like half the elements will equal, like will be like dependent on the other half. So the total number of unknowns will be dropped by almost 50%. And the reciprocal network is a network that doesn't include any active device, like no transistor, no diodes, no amplifier, and non-reciprocal media, like ferrite material or plasma. If this is the case, it's like all passive circuit, it's reciprocal, and in this case, Z matrix and Y matrix will be symmetric. If the network is lossless, so there is no losses, we can show that all the elements are pure imaginary. There is no real component in Z nor Y, so there is no losses. If those reciprocal and lossless conditions are there, the number of undefined parameter or the number of degrees of freedom in the Z and Y will be reduced like dramatically. So for the proof of these two conditions for lossless and reciprocal network, I'm not going to cover in the explanation, but you are welcome to read it from the textbook. Now let us like practice or like do some exercise on this. We have like this shown network, and we would like to find the Z parameters of this T network shown on figure. So we just put the circuit and apply the definition. So Z11 equal V1 total voltage divided by I1, the current going in port 1, when all other ports are open. So I2 is open circuit, and we need to find V1 and divide it by I1. So if we put some current here, the current will go in like this, and of course this is open, so no current will go here, and based on this current that's inserted at port 1, we measure V1. So V1 will equal I1 multiplied by ZA plus ZC. So V over I will equal ZA plus ZC. Same thing for Z22. Z22 is defined when we have a current going in port 2 while port 1 is kept open circuit. So the voltage over current in this case will equal ZB plus ZC. The other parameter that we want to measure is when we have I2, so there is a current going from I2 while I1 is kept open, we would like to measure V1 in this case. Okay, so V1 over I2 when I1 equals 0 or port 1 is open circuit. So we put a current here. The current would equal I2. It will go here, and we need to measure V1 because there is no current here. V1 will equal the potential over this element, which is ZC multiplied by I2. When we divide this by I2, it will equal ZC. So Z12 would equal ZC. We can calculate Z21 the same way. We put I2 equal, like Z21, we put I2 equal 0, and I1 will be the current going here, and we'll find that it's ZC because this is, like, we'll find that Z12 equals Z21 because this is a passive, like all passive elements, so it is a reciprocal circuit. So after the introduction of Y matrix and Z matrix, like, we have like very good tool for analysis, but this was not enough for like handling more general microwave circuits. So there is a need to define like a different tool. Why do we need to define like more tools for analysis? Because sometimes it is difficult to define voltage and current for non-TEM modes. Also, practical problems exist when trying to measure voltage and current at higher frequency, and because of that, scattering matrix is introduced. Scattering matrix is relating the incident and reflected and transmitted waves. So incident wave, reflected wave, and transmitted wave. The scattering matrix provides like a more complete description of the network as seen at its end ports. The scattering matrix relates the voltage waves incident on the port, and those are reflected from the ports. For some circuits, the scattering parameters can be calculated using network analysis. Otherwise, and this is another reason why scattering matrix is important, is in other cases the scattering parameters can be measured using vector network analyzer. By calculation or by measurements, once we have the scattering matrix, there is like a known mechanism to convert to other matrices, like, so we can convert from S matrix to Z or Y matrix and vice versa. So what is the scattering matrix? Again, we're gonna deal with our N-port network, and scattering matrix is relating the incident, positive is going in the port, and the reflected wave, negative, is going out of the port for the N ports. Again, if any physical port does have more than a single mode, it will be represented like if any port, any physical port carries, for example, like two like modes, it will be represented in the network as two boards, two electrical boards. So the boards here are not the physical boards. The boards here are the electrical boards. So each board represents a single propagating mode in a single physical board. Okay. So this is the general expression or the general format of the scattering matrix. The definition of element Sij is Vi negative divided by Vj plus when all the positive equals 0 except for the J element. So in words, Sij can be found by driving port J with an incident wave Vj plus and measure the reflected wave at port I when the incident waves on all other ports except for the J port equals 0. And this happens when all the other ports except J are matched. So when the port is matched, any signal that goes to this port, it will be absorbed and nothing will be reflected back into the network. So for example here, if this port is matched, any power that goes here, it will be absorbed, nothing will be reflected. So there is no positive signal, or there is no power going in that direction. If this port is matched, the only way for the signal is to go out and be absorbed by the matched load. Nothing is reflected. When nothing is reflected, then in this case, for example, V3 plus equals 0. So if we have, for example, like V4 is non-zero and all the others V plus are zeros, it means that all of them are matched. So the signal goes from 4. Anything that goes in this direction will be absorbed by the matched load. Nothing is reflected, nothing is reflected, nothing is reflected. So matched means V plus at this port equal 0. So the reflection coefficient looking into port N will equal SNN in one case, which is all other ports are matched. The transmission coefficient SNM between port M and N will like be meaningful, or like will equal SNM if all other ports are matched except for port M. So even port N is matched, but port M is the only one that is not matched. Under this condition, SNM will equal the transmission coefficient. And we can discuss why. I already explained, but we can discuss it further in our discussion session. The tool that is being used for the measurement of the scattering matrix is the network analyzer. This is a picture for one network analyzer. So the network analyzer measures S matrix. Network analyzer is characterized is a device that characterizes, or like a device or an equipment that is characterizing a device or network. Can be scalar, measuring only the magnitude. It can be vector, measuring phase and magnitude. This is a schematic for the network analyzer. For example, like this is the case for like 2 channels. We have like the source. The source is a function of frequency. We like launch the signal from the source. It will go into the network or device under test. And we are measuring the reflected from this port and the transmitted to the other port when it is matched. So we measure the reflected and divided by the incident. This is S11, for example, in this case. We measure the transmitted or divided by the incident to calculate S21. And this source is also like we can have like a match here and a source here. So this is like how it works. The main features for a network analyzer is its dynamic range, how small, what is the ratio between the maximum signal it can measure and the minimum signal it can measure. So of course the maximum signal it can measure like in dB is 0 dB, but I'm talking about like even the absolute, how much power can be measured, and the dynamic range, what is the ratio between the maximum it can measure and the minimum, what is the frequency range, what is the number of channels. So if the number of channels is 2, you can only measure like 2 port networks. If the number of channels are 4, you can measure like 4 port networks, so on and so forth. The output or the scattering matrix is produced in a number of formats. Touchstone format is a very common one. It's like a text format, and many modern network analyzer does have like post-processing capability, like time domain reflectometer, FFT, time domain measurements, so on and so forth. Okay, so now we know the definition of the scattering matrix. Let us apply this with an example. So we need to find the scattering parameter for this 3 dB attenuator circuit. So this is the circuit here, 8.56, and we have 141.8 ohm here. This is port 1 and port 2. Okay, you can of course like see this is all passive elements, and it is reciprocal. And here like we will need to like terminate a port with a matched load. So we're going to assume that the impedance is 50 ohm. So the matched impedance is 50 ohm. So if we want to have like 0 V2 plus, we need to put a 50 ohm here. If we need to have V1 plus equals 0, we need to put 50 ohm here. So matched termination. Okay, so S11 can be found as the reflection coefficient seen at port 1 when port 2 is terminated. Port 2 is terminated to 50 ohm, so no reflection, no input, no V2 plus from port 2. Under this condition, we need to find the V1 minus divided by V1 plus. So the input impedance here would equal like Zn1 minus 50 divided by Z1n plus 50. So if this is a 50 ohm, what is the input impedance here? It will equal this resistance plus this resistance in parallel with 8.5 plus 50. So we'd have, let us say this is RC, so it's RC multiplied by 58.56, so we have like here a 50 ohm divided by the sum, and in this case we find that Z input equal 50 ohm, so applying here S11 will equal 0 because of this symmetry. Also S22 equal 0. So this is like the first two parameters, S11 and S22. Now we need to calculate S21 or S12 because it's reciprocal. It would be the same value. So because S11 equal S22 equal 0, we know that V1 negative will be 0 when port 2 is terminated in Z0 equal 0, equal 50. So under this condition, when port 2 is matched with 50 ohm, V2 will equal 0. in this case we have V1 plus equal V1 because there is no reflection. S11 equals 0, so V1 negative in this case would equal 0, so V1 plus equal V1. And there is no V1 plus in this case because it's matched, so V2 will equal V2 negative. So applying V1 at port 1, we need to find V2 across the 50 ohm. So the network would be like 50 ohm here, and we are applying a potential here. We need to find what is the potential on this like termination. So we have V1, it will be, we know like these two like parallel, like 141 in parallel with 58, it will equal 41. So the voltage here will be applied for 8.56 and 41, which is this part, and this is the current, and there is a potential difference between 50 and 8.56. So just doing the math, it's a straightforward like circuit theory. We find that the ratio S12 or S21 will equal 0.707, which is like a 3 dB. When we go for the power, it's a 3 dB. So the input power is V1 plus square over 2 Z naught, which is 50 ohm. The output power is V2 minus, because it's matched in this case, over 2 Z naught. Just applying this condition here, we'll have the ratio between the input power and output power is half, which is minus 3 dB input of the input power. Regarding the conversion from S to Z or from Z to S, and if we know like how to convert from S to Z, then just Z minus 1 will equal Y, or if we are converting from Y to S, we can have Y minus 1 equal Z, Y to the power minus 1 equal Z, then we convert from Z to S. So at port N, so this is the mass for port N, the total voltage equals the positive, the incident and reflected volt summed up. The input current equals the input, the total current equals the input current minus the reflected current. For convenience, or like make it easier, we can put Z naught for port N to equal 1. So writing the Z matrix relation, the voltage matrix equals the Z matrix multiplied by I. So the I matrix can be written as V plus minus V minus. So the right hand side will equal this expression, and the V can be written as V plus plus V minus. So both the positive V plus in the same side, so we are bringing this here, it would be Z V plus minus V plus, and Z V minus plus V minus, and using the unity matrix, so the equation will look like this: V plus like Z minus unity multiplied by V plus equal Z plus unity multiplied by V minus. So like the V minus here, we just like multiply both sides by the inverse of this matrix. So the inverse of this matrix multiplied by Z minus U will equal the S matrix, because V minus will equal Z plus unity to the power minus 1 multiplied by the Z minus unity, and we can show that Z will equal this expression. So there is a direct mathematical way to convert from Z to S and from S to Z. If we can transform from S to Z, we can transform from S to Y and vice versa. If the S matrix, if the network is reciprocal, so S will equal S transpose. If the matrix is lossless, S transpose multiplied by S conjugate would equal unity. The proof of that can be revised from the textbook. So let us have this example about the usage of the scattering matrix. We have like a two-port network that does have like the following scattering matrix, and we have like three questions. Determine if the network is reciprocal or lossless. If port 2 is terminated with a matched load, what is the return loss seen at port 1? If port 2 is terminated with a short circuit, what is the return loss seen at port 1? So for the first question, is it reciprocal or not? It's very clear that it is not reciprocal. Why? Because S12 doesn't equal S21. So S doesn't equal S transpose. There is a phase difference here. And to determine if it's lossless or not, we need to like transpose and multiply with the conjugate. And when we do that, we'll find that it is not unity. So the network is not reciprocal and it is not lossless. When port 2 is terminated with a matched load, so V2 plus will equal 0. The reflection coefficient, so like here we have we have okay, let's have this pen. So here we have V1 plus and we have V2 plus. If V2 is matched, what will happen? This will equal 0. So under this case, S11 let me bring so in this case S11 will equal 0.15 and what is requested is the return loss. So the return loss is minus 20 log the S11 in this case, which is 16.5 dB. Now for the third requirement is when port 2 is terminated. When port 2 is terminated with a short circuit, we know that the reflection coefficient for the short circuit is minus 1. So the relationship between V2 plus the incident and V2 reflected, V2 minus, is minus 1. So writing V1, so writing the scattering matrix into equation, V1 will have this expression, V2 will have this expression, and if we just substituted V2 plus as minus V2 minus, we'll have this expression here. We know that V2 minus, and so from this equation here, we have V2 minus here, we have V2 minus here, so we can relate V2 minus to V1 plus and come up with this expression. Then we take V1 plus and replace it here. So V2 minus here will replace it by this expression. So the first equation V1 minus will equal S11 V1 plus minus S12 multiplied by V2 minus here. So we'll come up with this expression. So the reflection coefficient here, V1 minus over V1 plus under this condition will equal S11 minus this expression, and we can come up with the value and we can calculate the return loss, which is minus 20 log to the power to the base 10 of 0.452, and the exercise is solved this way. Many times, especially when we do measurements, we might need to have like a shift in the reference plane. As we discussed like earlier, for each board we have like a reference plane where the phase is defined to be 0 here. In some cases, especially when we do like measurements, we might need to like move the reference plane. For example, if we have like n boards and each board would have a definition for the reference plane, let us say this point here, for some measurement reason or like adding cables or whatever, we need to like move the reference plane to another point, which is L1 away from the original reference plane. So we need to find the effect of this translation of the reference plane on the S matrix. So the original S matrix measured at the original S reference plane is S. The scattering matrix after moving to the new reference planes is S prime. So what we have is that like S is V minus and relating to V plus, S prime is the definition at the new reference plane. So here, for the incident wave that is like L meter away from the board, would have the positive multiplied by e to the j beta n ln. Beta is the propagation constant or the phase constant. Ln is the displacement of reference plane for board n away from the reference plane. For the reflected, it is negative because it is in the direction of its propagation. So V plus and V plus prime are related with this expression. V minus and V prime minus are related with this expression. If we like go here and use this expression here, V minus equal V prime minus multiplied by this phase, we can come up with this diagonal matrix before V minus, another diagonal matrix before the V plus, and this is S. What we want is S prime. S prime is the relationship between this vector and that vector. In order to reach this, we multiply both sides by the inverse of this matrix. Doing that, because it's a diagonal matrix, we'll find that the prime, which is the reflected wave at the new reference plane, and the prime, the incident waves at the new reference plane, is related to one another with this relation. So this expression here, this matrix S matrix, equal the S prime. So this is the effect of a shift in the reference plane. So even after like introducing the scattering matrix, it was found that it is not solving all the problems. There is some cases that it is difficult to like apply the scattering matrix, like this case of a load, of a generator connected to some circuit without any transmission line. So some new idea is like introduced to make the scattering matrix a more general tool. So like cases like having non-real characteristic impedance, when the characteristic impedance is complex, doesn't fit the like the current structure of the scattering matrix, and also when we have no transmission line nor waveguide into the circuit, it's hard to use scattering matrix. So the search for a new or a more general scattering matrix was needed, and they reach like a generalized scattering matrix that using Bauer waves. So the Bauer waves is defining incident Bauer wave and reflected Bauer wave. Incident Bauer wave is A, reflected Bauer wave is B, and the definition for A and B does have this expression where ZR, the reference impedance, can be complex, and based on that, V will equal like this expression or this relation between A, B, and reference impedance. Current would equal this expression, and under this expression, the power delivered to the load equal half the amplitude square of A incident power minus square amplitude of B, which is the reflected power, and the power reflection coefficient here would equal B over A. So with this introduction of a generalized scattering matrix, we can like measure incident power, reflected power, and measure the scattering matrix even if the network is lossy, even if the network doesn't have a transmission line or waveguide involved, by the definition of voltage and current with this way, using the incident Bauer wave and the reflected Bauer wave. And this is the learning objective of this lecture. Thanks for watching the video, and meet you in the discussion session. Goodbye.